Your molecular structure is really something fine. A first-rate example of functional design. Those cosmic undulations are steady coming through. Your molecular structure, baby.
Good morning. It's 7:30 on Friday morning. I've just done part of this lecture once, but have forgotten to hit the record key, so I'll do it again. And today I'd like to tell you about some stereochemistry issues, maybe group transfer polymerization, and then also maybe something about radiative polymerizations. But we'll call this section E. I told you leave a spot for it. We'll call it stereo chemical concerns. CE. Okay, so in particular, wait, where'd it go? Oh, it's up there. Okay, sorry. So in particular, we'll talk about conjugated dienes first. But before I do that, just remember that in principle, you can hit the stop button. You can go back and play this partially over again if you didn't understand something. There's some options for you. So the first thing that we're going to consider are conjugated dienes. So we're interested in butadiene, isoprene, etc. Now, if butadiene and isoprene don't ring a bell when you think about structures, go back and write them down and put them in there. All right, first set we'll talk about our cis-trans tactic. It's the amount of cis and trans that we have in these molecules. So let's look at butadiene. And butadienes going to form, for example, I'll just draw parts of the molecules here. This structure, which we would call the cis 1,4 structure. Obviously, this is the material which is the better rubber, as we know. But in addition to that, essentially you get the chains reacting to extend on the 1 carbon and the 4 carbon. Then you can also make the trans 1,4. If this were isoprene instead of butadiene, we would want to call one of these natural rubber and the other one gutta percha rubber, but this is the trans 1,4. Better is always relevant or relative to what properties you're interested in. So to say that the cis is a better rubber probably isn't accurate, but at least it's more rubbery. Okay, next one. We would have a situation where the double bond would just act as a single double bond and not in a conjugated fashion. So what we would be left with is a double bond hanging off the end, and that would be a 1,2 addition. So just one of the double bonds would react, and the other one would just hang off the end. And this guy hanging off the end could also react later forming what I might call the 3,4 addition. Okay, so what I want to do is I want to look at alkali metals and what I want is to put the percentage of different species formed by these metals. And in the first case, I will do these for isoprene. So, with isoprene, if your and let's put the metals down here, we'll have lithium, sodium, potassium, rubidium, and cesium. So what we've got is like butyl lithium, butyl cesium, etc. So, turns out that you get 94% cis if you do lithium. You wind up with 0 trans, 0, 1, 2, and 6% 3, 4. For sodium, you get 0, 43, 6, and 51. Potassium, 0, 52, 8, and 40. Rubidium, 5, 47, 8, 39, and cesium, 4, 51, 8, 37. Now, let's switch, and instead of isoprene, we'll do butadiene. And I will try to put these in between here. So the red ones will be for butadiene. 35, 51, 13, and I believe the dash means wasn't measured or wasn't found. Okay, sodium, 10, 25, 65, and in all these cases, these are non-existent. So I'll just ignore those. In any case, potassium, 15, 40, and 45. Rubidium, 5, 47, 8, 7, 31, and 62. And lastly, cesium, 6, 35, and 59. Okay, so when we look at this table all at once, one of the things that we find is that you can have really decent control over the reactions at different times. What's the reason for all this? And by the way, the take-home message is that organolithium gives a high cis content. Okay? But in addition to that, it's probably due to the fact that lithium is an ion which is small enough that you can that it can kind of get in there, and the conjugated double bond can kind of wrap around it, giving you the cis isomer. Okay, my screen just went blank. So now we're back in business, and let's do something about B two monosubstituted vinyls. I'm going to draw a couple structures here, but obviously the isotactic polymer is one. And for the isotactic polymer, let me just see if I can draw it this way. The second one that we'll draw is the syndiotactic polymer. And obviously the third one that we'll draw is the atactic polymer. I can't draw enough of these to really do justice to how complex that it might be, but I'll try. Okay, so obviously for the syndiotactic polymer, if we're dealing with something like polypropylene, when we lay this out in whatever this is, a Fisher projection, I guess, all the R's are on the same side. And it probably doesn't surprise you that this particular material, if for example it's polypropylene, it is mostly crystalline. With a melting point of 160 degrees. Sorry, it's one here. Melting point 160 degrees. And this is likely to be something you could do via some kind of coordination reaction. Syndiotactic, there we have the R's on the different sides. I don't have any numbers for that. If I remember to look them up, somebody see if they can look up what syndiotactic polypropylene has as a melting point. And if you would, let me know. So here, this is mostly non-crystalline. Has melting points of around 75 degrees C, but it still has got a little bit of crystallinity in it. And this is what you would get via free radical. But I'm going to cross that out. because you only get oligomers, but the oligomers tend to be mostly non-crystalline anyway, but ionic can go to give you some that's kind of atactic. But with polypropylene, a lot of it's made with coordination polymerization. But remember, they can put all kinds of additives in it, other comonomers, to make it non-crystalline that way. Okay. In addition to that, there are three. There are di-substituted. And for di-substituted, there is a erythrodiisotactic. You can guess there's also a threodiisotactic. And then there is a disyndiotic. And then there's there's D here, which is others. Where did others go? Sorry, I see others down here, but I don't see it up there. Oh, there it is. Okay. Weird. Something's fishy. Oh well. Okay. So let's draw a couple of these. I won't draw others. So these are di-substituted, so it would be something like this. You can also have where obviously the R's and R primes alternate, and then you can have them alternate by pairs. I'm not going to get into how you prepare them. Because I don't know. And it's kind of a detail, but you can do it if you need to. And by the way, remember, you can stop the video when you need to and go on. All right, so the next item is control. You can have some control over these. Let's look at the synthesis. Oh, and I should say that anionic polymerization of polar monomers in polar solvents only get poor specificity. But anionic polymerizations in apolar solvents can be very specific. So if the polarity is high, you get a lot of separation between things, and consequently you don't get specificity, but where things are kind of paired, charges kind of lumped together a little bit, things are close together, there you can get stereochemical control. So we'll look at PMMA, and we're doing the reaction in minus 30 degrees with N-butyl lithium. And what we're going to do is we're going to look at solvents. So we're going to look at toluene and the ratio with dimethoxyethane. All right, so we're going to look at, oops, running out of page here. So we're going to look at 100 to 0. We're going to look at 64 to 36. We're going to look at 38 to 62. We're going to look at 2 to 98. And we're going to look at 0 to 100. So pure toluene to pure dimethoxyethane. And the parts that we're going to look at is we're going to look at the fraction of isotactic dyads, the fraction of isotactic syndiotactic, actually these are triads, but that'll be later. And we're going to look at the fraction of syndiotactic. So, with 100% toluene, 59, 23, 18. Add a little bit dimethoxyethane, more polar, 38, 27, 35. Get more polar. Ooh, sorry. 24, 32, 44, 2% toluene, 16, 29, 55, and 13, 25, 62. Okay, so what you see is that in toluene, you get large amounts of the isotactic polymer, and as you add dimethoxyethane, more polar, you wind up getting more of the syndiotactic. And there are lots of examples of doing this kind of stuff, and I don't want to get into them too much. Okay, so that's all for this E. The next section here is F, group transfer polymerization. I was planning to skip this, but your book has a section on it, so I figured I would include it. And group transfer polymerization has this has a abbreviation GTP, and Webster and co-workers did this at DuPont, and this was published in JACS 1983, 105, 5706, and my acquaintance Dotsi Soga and Webster published this in the Journal of Polymer Science, Polymer Letters edition. (1983). I don't have the full reference on that. Okay, so as far as general features are concerned, it occurs with the transfer of a trimethyl silyl group on the living end. Oh, by the way, now I'm thinking about it, I forgot to mention that when we talked about anionic polymerizations, if you keep those living polymers alive and you don't terminate them, and you keep them away from air, like when you make styrene butadiene block copolymers, they could last for a long time, years, as long as you keep them dry and CO2 out. Okay. N groups live for long lives under moderate conditions. And many monomers can be used. And including this is one that's hard to do otherwise, including alpha beta unsaturated esters. Ketones. And nitriles. And carboxamides. Okay, so quite a few. Look up if you're not familiar with each of those groups. Look them up so you know so you have an idea of the structures. D. Monodisperse. I'm going to put that in quotes because they're never really monodisperse like a protein might be, but they're low polydispersities, small polydispersities. So monodispersed polymers may be obtained. And because they're kind of living, block copolymer is possible. Okay, so 2. Initiators. Okay, the initiators are things like this. Okay, so it's got a trimethylsilyl group on it. Also stuff like similar. Oops. Like that. So, oh, and this first category, sorry, I didn't have the label here. So A would be dimethylketene methyl trimethylsilyl acetal. Dimethyl ketene methyl trimethyl silyl acetal. Or so they tell me. You could tell me that name wrong and I probably wouldn't know the difference. Second one, trimethyl silyl cyanide, group CYAN. And this guy is just simply I want to do it this way, right? Wait. I think it's this way. I don't think it's with the C reversed. I had it backwards in my notes, but I think that's right. Okay, next one. C ethyl trimethylsilyl acetate. And that has the structure there's a trimethylsilyl group. And then D. I don't know if I want to write this out, but it's 2-methyl-1 square brackets 2-trimethylsilyl ethoxy n square brackets 1-propenyl oxy trimethylsilane And I'm just going to draw the structure, 2 methyls there, double bond. And down here, oxygen, 1, 2, 3, 4, oxygen, Me3. Okay. By the way, this is kind of a protective end group too. So, there's a lot of trimethylsilyl groups in here. And so, you need, you need 3 catalysts. And these catalysts are bifluoride, trimethylsilyl fluoride, difluoride, cyanide, I guess azide, and then the big thing is the mechanism. Okay, as far as the mechanism is concerned, and this gets a little, there's a lot of arrows going on here. So I think what I'll do is I'm going to draw it like here, or at least attempt to. Okay, so in fact, I'm going to go down to the next page here so I give myself enough room. Got double bond there, oxygen, methoxy, and the 2 methyl groups there. So this coordinates to the silicon, and this silicon, for example, can have a nucleophile and some other methyls. And silicon has extra electron density, so move up a little bit. This would obviously be the case for methyl methacrylate. And so what happens here is the mechanism is that this bond is formed and this guy goes there. Oops, that didn't work out too well. There we go. It's kind of a concerted reaction. And so what you're left with, I drew this really big. So, oh, and this whole thing is a -1 charge. So the next step here is to form the species. Okay, so what we've done here is we have, in effect, inserted a methyl methacrylate chain inside of the growing end, and now I have a silo group at the end of the chain, and that can react further in the same way. And this is known as a two plus two plus two plus two addition. Okay, now B is propagation. If you look at the molecule, you can see that you can do this in kind of a similar way. So there's the end, and you got this. Trimethyl silo group. And it can add to another monomer. In the same way, there's your methyl methacrylate. Probably should do it this way. Probably should make this bigger, like that. There's your methyl methacrylate, and what you wind up with is and you wind up inserting one or more methyl methacrylate groups in there. And attached to the end is this trimethyl silo group with the double bond. So this is a material which then is trimethyl silo terminated. These are reactive, but they're not super reactive. And the mechanism studies show that the group transfer occurs rather than silo group exchange. In other words, it's not that the silo group comes off and another one comes on. That's like the case in raft, but here you actually get kind of an insertion. These molecules tend to have living ends. So you get termination of the living ends, terminatation, termination of the living ends, and you get oops, I don't like what I just drew. Sorry. Let me just cross it out. That's the CH3 from the backbone. And then the living end there. You can kill it off with stuff like acid. If you kill it off with acid, then it forms R, CH2, CCH3. You wind up putting a hydrogen on there. And basically, or other proton donating substances. Okay, and so if you can make a material like this, you can make a black copolymer. And a couple examples of this would be on how you would do this is let's look at how we make MMA, and we'll look at initiators, catalyst, solvents, Mn and Mw, which we'll talk about later. And then we'll call this the polydispersity index, which is just the ratio of Mw to Mn. We'll do that later. So the initiator, need a little room for the initiator here. There's the initiator, catalyst. Let's see where, okay, so catalyst. TASF2, it's one of the catalysts we talked about before, SIME3. And we do this in THF at -78. Let me move this down a little bit. I didn't really leave myself enough room here. Sorry. Okay. 1120, 1750, polydispersity index of 1.56. Same catalyst, or same initiator. Catalyst is the azide, TAF2N3. And I guess that's acetonitrile. 3000, 3100, and 1.03. Good molecular mass control there, certainly. Same catalyst, same initiator. Oh, I'm obviously off by 1, am I not? Jeez. Okay, let me straighten this out. Not that way. It's hard sometimes to keep registry on the iPad. There's solvent. There's MN. There's MW. And there's that. Okay. So, catalyst, we move over there. Solvent, we move over there. 3000, we move there. And these guys move there. Okay. Next. Same deal. We have now, I don't know what TAS is. But again, acetonitrile. Another example is 1700, 1900. Polydispersity of 1.10. Just the last one. You're getting sick of these by now, I know. But again, it's MMA. And now we have MESICN. Catalyst is TASCN, so it's the cyanide. Solvent. Acetonitrile. MN 800. MW 800. 1.03. Obviously, there's some significant figure going on there, but you're able to produce, in general, medium to low molecular weight polymers, but they can be done very fairly monodisperse under the right conditions. And one more comment is that most other acrylates and methacrylates work. What DuPont made these for was for coatings. And so they were putting it into their automotive coatings division. I don't know what ever became of them, if they're still being regularly used today or not, but it's a nice polymerization mechanism that's rather different than some of the other ones. I should also point out that some people have uh, suggested that rather than being a new label of group transfer polymerization, although that has stuck, is that others have wanted to call that a Michael insertion polymerization. But nevertheless, I consider it to be a moderately uh, interesting and well documented reaction mechanism. And DuPont got a lot of mileage out of it in the 80s. So, okay. All right, so I got a few minutes left. Let me talk a little bit about H, radiative polymerization. Why? Because I think it's cool and has certain advantages. Those advantages include often it's instantaneous. You have instantaneous control. Basically, the radiation hits it and does its thing almost immediately. Usually, there's no initiator needed. Well, sometimes you can put sensitizer in. Why? Because you don't have to add anything special in there. Why? Because some high energy radiation comes in and it just knocks electrons around. And so it can knock it around in a traditional initiator. It can knock it around in the monomer. So it gives you access to a wider range of temperatures. So, for example, um, depending on the mechanism, if you generate a free radical low temperature, because propagation does not occur rapidly, you are able to start the initiation at low temperature and the propagation goes at low temperature. Sometimes it is site specific. Um, Depending on the radiation, for example, if you have some dangling double bonds, like in a 1,2 addition of butadiene, you can activate those selectively. You can also use this stuff for sterilization. And packaging. So it has some real advantages. There are some disadvantages. Not all monomers are reactive. So sometimes you actually could use an initiator or some kind of sensitizer. Let's put a note there. I know I told you that you didn't need them up above, but sometimes you do. But most of the time you don't. The biggest problem with this is generally that you need a source. So depending on what you're going to do with it, you've got to figure out how to deal with it. You got to figure out how to buy it. So these tend to be expensive. If it's an electron source, it's still expensive. If it's a neutron source, you need a nuclear reactor. These are complex, and you need some kind of shielding. And often you get nonspecific reactions. The higher the energy, the radiation, the more random the reactions are. If you hit something with high energy gamma rays, they just knock electrons out all over the place. And consequently, it's just tough to do. So, let's look at a couple sources. Okay, I'm going to try and do a chart again. I've had mixed luck with my charts so far. But here we'll do radiation. The kind of radiation here. We'll do the wavelength in nanometers. We'll do the energy. In megajoules. And we'll do the application. Okay, so we can use gamma rays. Okay, gamma rays are just really high energy. I'll put a list A there, and I'll add some notes down below. A little later. But, okay, so if you've got gamma ray radiation, the wavelengths here are on the order of 0.001 nanometers. So the energy in megajoules are on the order of 117,000 megajoules. Huge energy. You can do polymerization with these. Okay, you can use electrons. Symbol obviously is beta minus. Oh, it looks like I got a big space here. Let me draw it closer. Okay, and these are approximate wavelengths. Oh, and this is an electron, which is about 150 kilovolts of potential. Reference B. So this is 0.008 or thereabouts. Energies, 15,000. so an order of magnitude lower in energy. Often electron beams are used for curing reactions. You can use ions. For example, an alpha particle. This alpha particle might be on the order of 20 kilovolts. An alpha particle is just a helium nucleus, right? We'll put a C here. And so 0.013 nanometers, 8,000, and you can etch resins. You can just knock surface layers off. Alpha particles don't often penetrate your skin, but they do penetrate your lungs. If they get them in your lungs. You can use electrons that are more on the order of 20 kilovolts. So this is D, B, and D, and 0.06, 20,000, wait, 2,000. 2,000. And photoresist. X-rays. X-rays tend to be moderately energetic. 0.1, 2.1. Energies, call it 1,000. Also used for resist. So you can etch away layers from it like a photoresist. UV. E. UV 100 to 300. 0.8, so we're going way down in energy, but still, this is a lot of energy for a bond. You can break bonds with this. Not all bonds, but you can break some. You can use UV again, 300 to 400 nanometers, so even less energetic. 0.4. Use that to cure printing inks. You can use lasers. Most lasers we have, of course, are indivisible. So on the order of 400 to 500 nanometers. Now you're talking about 0.25. Holography and photoresist. You can also use lasers. I don't have the number, about half of that. Yeah, 1060. 0.013. Some of these lasers aren't very good. I mean, they're not very strong, but you can use them for plastic volatilization. If you got the right laser and you got somebody that can show you a demonstration, sometimes they like to take some of these lasers and just stick polystyrene peanuts in there and watch them explode. So a couple notes. A, cobalt 60 is where you might be getting gamma rays from. They're at about 1.25 mega electron volts. It has a tau 1/2. Half-year life of cobalt 60 is about 5.27 years. So it's not super radioactive, but it's fairly radioactive. That's probably the most common. B, if you're going to use these electrons, you often will use a linear accelerator. And that'll be about 0.95 to 10 MeVs. Kind of expensive to maintain. If you're doing C, if you're doing alphas, you can also do those from a linear accelerator, and 3 to 600 MeVs. Sometimes you need a lot to get an alpha particle going. D, electrons. You can do a lower electron, you can do a Van de Graaff generator. These are the things that you can touch and cause your hair to stand on end. You've probably seen those. Those typically are 1 to 5 MeVs. No, you don't have to memorize these if you're wondering. And you do x-rays from an x-ray machine. .05 to 0.3 MeVs. Okay, so screen just went blank. Okay, let's do a couple examples. How are we doing on time? Okay, not too bad. Got a few examples here, but some of these are actually pretty cool. Okay, so we'll call this section 4, monomers and examples. Okay. A, high energy radiation. Most monomers are susceptible. That's because they're so high energy that you just knock stuff around. These are often free radical reactions. You can do grafting in the solid state. If you're doing a grafting reaction, you sometimes have to be able to get a whole bunch of, You may get a whole bunch of reagents down to do the grafting. Here, if you got some active groups in there, you just activate them with radiation, and it can go. PMMA. When I did this last, there were approximately 2,000 tons per year that were made this way. It's not a lot, but it's some. And then there's a fair amount of cross-linking and chain scission that's done. I'd be curious if that's how PEX is made, with some kind of radiation. Okay, so B, UV visible. Some electrons too, 300 nanometers or longer. You can polymerize vinyl, alkyl, ketones. Or vinyl bromide. Excuse me. Apparently in ancient Egypt, mummies were wrapped with the oil of lavender and bitumen of Judea, and then they were set out in the sunlight and exposed to the UV light, and that caused the polymerization of the oil of lavender. Just a little side tidbit there. You can do 300 nanometers or shorter. And you can polymerize styrene, MMA, isobutylene, at 117 or 123 nanometers. You can also make 2-ethyl hexyl acrylate. Some of these get tough because they don't propagate too well when you just do regular free radical. Or 2-hydroxypropyl acrylate, plus others. So a variety of photocurable inks. You put ink on the page, you hit it with UV, and then you get the polymer to cross-link. You can make fingernail enamels doing it that way. You can take some of the printing ink, neopentyl glycol diacrylate, plus vinyl pyrrolidone, benzoin ether and benzoquinone as a synthesizer, plus a pigment, and you get smudge-proof ink with strong UV in seconds. So that's one of the ways that they can print newspapers so fast. If you think about that, they usually have liquid ink going on the page, and then it comes out the other side on the newspaper and it's dry, so they can do photo curing. You can also do vapor phase deposition. So, for example, you can take tetrafluoroethylene. If you have 10 torr with UV, 185 to 300 nanometers, you can produce a clear film of Teflon. It's not exactly Teflon, but it's close enough. If you have greater than 10 torr, you get a white, powdery fluff. And that material contains CF3 groups and has different properties than Teflon because with the irradiation, there is some rearrangement. You can do hexachlorobutadiene. with hexachlorobutadiene, 200 to 300 nanometers. You get thin films. And they are electrically and mechanically continuous. So you can make a conducting film on the surface. One of the ones that actually gets used a bit is the production of polyvinyl cinnamate. So that material is CH2, CH, N, O, and then this guy. So it's got a big phenyl group on there, and it's usually made with an ester interchange of PVAC. And this material produces a cross-linked network which is not washed away. So it's a tenacious network. And so when you etch photographic or lithographic plates, like when you make photoresist and things like that, this one does not get washed away. And it's also used as on the phosphor of TV screens. So there's a large use in lithography. Now, a couple more quick examples, then we'll finish. Famous last words, right? Quick examples. You can do plasma polymerization. Basically, what you do to do plasma polymerization is use an ionized gas. Kind of like what you would get in a fluorescent light, only much more intense. So you get ions in there, you get neutrals, and it's just a glow discharge, a kind of glow discharge tube. And you put some monomer in there, and you can use conventional monomers or you can do unconventional monomers. So you can polymerize ethane. Okay, you normally think ethylene, but here you can do ethane. You can do tetrafluoroethylene. You can add CO. You can add H2. Well, I should say these are just things you might add to the mix to control how much hydrogen, nitrogen, and oxygen you have. And you can just polymerize the whole mess. You can do stuff with double bonds. You can do aromatics. And you can do amines. You can do nitriles. You can do stuff with alcohols, ethers, carboxyl groups. chlorine groups, but they're a little harder. And then, of course, you could do traditional monomers like ethylene, and you can make a polymer from that. So you take ethylene, you put a little bit of it in a glow discharge tube, you put in a radio frequency, and you get a plasma going. You see a nice blue light. Could be violet light, and the ethylene polymerizes. When you do that, you also get a whole bunch of different groups. It's not just polyethylene that you get. You can basically get a cross-linked material, and for example, you can have ethyl groups on it. So all of the monomers you put in there kind of get mixed up a little bit. The approximate formula is there's CH2s plus CH3 groups. And by adding in hydrogen and ethylene and ethane, you can change the amount of aliphatic and aromatic hydrocarbons you get in your coatings. These things generally produce continuous pinhole free coatings. It can be used for a number of things like reverse osmosis. Okay. Given the time, I didn't quite finish this section, but I think this is about the right place to stop. So I'm going to stop now and just talk about a few examples, maybe a little later, either in an additional video or in class. So till then, thank you, and I hope you learned something.